All right, hi everybody. This is going to be our lecture video on simple harmonic motion, and I'm also going to attach a little bit of information on pendulums, so there won't be two separate videos, there will just be this one. I'm going to try and keep it short. Our lectures are never usually very long. A lot of times what we do is we kind of look and then we start doing, and you guys have already been doing when it comes to this stuff. This is just kind of information I want to make sure we've retained from this particular chapter. And so our first big topic is going to be on simple harmonic motion. What that means is just an oscillation of some kind. Now, we've looked at springs before, and on our screen we see a spring that actually can slide. What we're making an assumption about is that this is a frictionless surface that this spring is able to slide on. You'll note that what they measure from, everything is measured from what we call like an initial position. From there, we can actually compress the spring or we can stretch the spring, and we can see what happens as a result of that stretch or that compression. Now, an oscillation is simply going to be defined as a disturbance from its initial position, so x equals 0, back and forth. So if you think about a spring, if you stretch it out, the one full oscillation would be when this spring crosses the 0 point, compresses, and then crosses the 0 point again and comes back to its original stretched position. And this same idea is going to apply to our pendulums later on. Now, for any oscillation, we can measure the length of time it takes for that back and forth motion. That back and forth motion is one oscillation, and we can measure the time it takes and call that the period of that oscillation. Now, amplitude in the case of a spring is going to be the distance from its initial position. So it's going to be how big is the compression or the stretch of the spring itself. The stiffer your spring is, so the stronger the metal is, or the more coiled it might be, the stiffer the spring is, the smaller the period is going to be. And I apologize, I tried to mute some of these things and I cannot figure out how to get some things to shut up on my other set of computers. But anyway, so what we're saying is then that the period of an oscillation is when it starts at one position, crosses its midpoint, or in our case, the rest position, and then comes back to that initial point. And that's the length of time it takes. That's the period. Okay. When it comes to springs, mass does in fact matter. When it comes to pendulums, that it does not. But with springs, if we add mass here, then what we're doing is we're actually going to have increase the amount of force that we're actually pulling on the spring or pushing on the spring with. Okay. Something to just kind of note is that everything that we study in this particular chapter is going to have some kind of oscillating or wave-like motion. In the case of waves, we could call one oscillation one wavelength. So from the crest of one wave to the crest of the next, or from the trough of one wave to the trough of the next, whatever we're measuring from, we want to make sure we're looking at one full oscillation. And in this case, most waves end up being sine functions. And a lot of the stuff we're going to study moving forward are wave-like functions. So things like sound and light are going to be the big ones that we cover by the end of this year. Okay, so that's just kind of something to keep in mind. So period, amplitude, and then the last thing we want to talk a little bit about is the frequency of the motion. And frequency is simply going to be defined as the amount of time it takes for a certain number of oscillations to occur. So in other words, frequency is how many oscillations actually occur and over a set period of time. Sorry. So period is going to be the time it takes for an oscillation to occur. Frequency is going to be how many oscillations can occur in a set period of time. So if I were looking at this car, how many bumps up and down, how many waves are we going to cross in 1 second? And that would be the frequency of that particular thing. And there are those formulas for both the period of a simple oscillator and the frequency of a simple oscillator. This is all from section 3 so far, so all of this should look sort of familiar to you. Another example of how we can actually translate a spring's motion into a wave-like motion is if we attached a pen on something that's kind of bouncing on a spring, we would see that as it bounced up and down, if we were dragging this paper at a constant speed, then we would see this perfect sine wave. And that's just, for some reason, this is the most common way that we have of demonstrating how a spring-like motion, which really all we see is a bounce up and down, becomes this sine wave-like motion. So just kind of keep in mind, anything that does this back and forth motion is considered a simple oscillator, and anything that has that back and forth motion, displacement from an original position, is going to be something that we can measure some kind of a sine wave on. So it has wave-like motion, if you will. All right, and then from there, we just have some different examples of how these springs would be measured. So if we're starting from a compressed position, let's assume that this is our compressed position, that very first one, and that this is our stretched position, and this is our equilibrium. You can see that if we compress it and then we release it, we're going to see it bounce downward all the way, bounce upward all the way, bounce downward all the way, upward, downward. There are a couple of things we have to kind of ignore, like gravity in this case, because eventually gravity would stop this spring from moving altogether and get it back to its original position. But as we're doing this, if we just look at the motion of the spring, it looks like a sine wave. If we attached a pen and dragged the paper like we saw in that previous picture, then we would also see this sine wave come out. Now, the period of that particular thing is going to be the length of time it takes to go from one crest to another. The frequency would be if we kind of held our finger in place here and we timed it for 10 seconds, how many oscillations would we see? We would do number of oscillations divided by the time it takes. So frequency always has an inverse sine, or an inverse time factor. So in other words, the frequency of motion can be measured in hertz, which also has a unit of s to the negative 1, if that's what you're, if we didn't quite get that from last week. All right, and then the next thing to talk about is just going to be pendulums. Now, pendulums, again, a fancy form of a simple harmonic oscillator. And there's a really good breakdown of the formula in section 4, which says that the period, so t, is equal to 2 pi times the square root of the length of the pendulum divided by gravity. So some things to realize here. 1, mass doesn't matter at all. No matter what you do, mass will not matter on your pendulum. You cannot change that. Now, the thing that I want you investigating this week is something in one of your virtual labs. Will theta matter? And the answer is going to be one that you discover. And that is going to be something that I am going to send in your quiz tomorrow. So make sure you do that before tomorrow. But that theta is going to have an impact. Unfortunately, we don't really know what the impact is. Even though it's not part of the formula, you're still going to want to go through and you're going to want to measure and see if there is an impact on theta of the motion of the period itself. Okay, I believe that that's all I have for you for the particular topics we've covered so far. Again, pendulums, simple harmonic oscillators of a certain kind, something that kind of swings back and forth. You guys are supposed to be making one in your lab this week, and you are still supposed to be, going through and doing the virtual lab as well. I recommend getting everything done for 16.2 through 4 before tomorrow, because you do have a quiz over this coming at you tomorrow. I will email it, and I will expect it back within the hour. Okay, that's all for today. See you later.